In this video, we're going to be drawing a distinction between Dijkstra's algorithm and Prim's algorithm. So these are both greedy algorithms that operate on graphs. Prim's algorithm tries to find the minimum spanning tree in a graph, and Dijkstra's algorithm finds the shortest path tree. So given a start node, we're going to find the shortest path to every single vertex, and we're going to keep upper bounds of paths and continuously try to improve them. These are both greedy algorithms. They both operate on graphs. They both create trees, but at the end of the day, they have different goals, and their greedy strategies optimize for different things. So we're going to perform both of them on this graph, and we're going to draw that distinction and make it really clear. First off, we're going to use Dijkstra's algorithm, and the way Dijkstra's algorithm works is we're going to keep a table of distance upper bounds. And each of these upper bounds are the shortest distance from the start. We're going to make the start A, the shortest distance, and continuously we're going to try to improve these as we go through the graph. And we're also going to keep track of the parent. This actually is a parallel you can draw to some dynamic programming problems. A lot of questions people have is, how do you track the optimal problem? Because sometimes you just find the number solution, like the maximum weight of a knapsack or something. The way that you would do that is you need to keep track of the winner at every optimal step. We would need a table to keep the parent that had an optimal solution. So we're going to create that table. So the way that Dijkstra's works is we're going to take the start as A. And as we're going through this, you're going to see the distinction. We already drew the distinction, which is the greedy choices are different, but it becomes really apparent as we go through both of these. And there's a lot of great resources to learn about both of these algorithms, Dijkstra's and Prim's, with the complexity analysis. So I don't want to go too deep into that. I'm just trying to draw the distinction here. We're going to add the first vertex, and we're going to mark the distance upper bound as 0. And then for every other vertex, we are going to give it a distance upper bound of infinity. We don't really know how far that vertex is. If at the end of this search, the distance is still infinity, that means that the item, that vertex, was not in A's connected component. If it's outside of A's connected component, then we can't reach it to find its distance to A. So ultimately, we can never improve that. So it'll stay into infinity. And now we're going to mark all of these vertices as unexplored. And what we're going to greedily do is we're going to process the vertex with the smallest upper bound on distance that has not been processed. So none of these have been processed, and the smaller upper bound distance is the A itself, which is the start, and it was set up this way. So we're going to process that vertex. So now we're processing on the A, and what we're ultimately going to do is we're going to look at every single edge coming off of A. So we have 1, 2, 3, 4. 4 edges coming off of A, and we're going to see, if I have A as the parent, will I improve the distance upper bound to any of these vertices coming off of the A? So is the distance to A, we're going to look at the first vertex B, is the distance to A plus the edge weight to B, which is 2. Will that give us a better cost than the current upper bound? The current upper bound on B is infinity. So 0 plus 2 is 2. And the min of 2 and infinity is just 2. In fact, it's actually a good way to go. We want to come from the A. So we're saying, if I want to get to B, the best way to get to B right now is A. So I'll mark the parent of B as A, and then the new upper bound on B is going to be what we yielded as the minimum here, which is just 2. So given that I choose the best path to B, the worst case work that I do in terms of cost is going to be 2. So now we can process the C, and we need to make sure we process all of these vertices. Process the C. What is the current cost to get to C, infinity? Can we beat that by going through A? What's the cost to get to A at maximum? It's 0. So 0 plus actually traversing the edge weight. We're looking at C, so we're going to do 4. So 4. So that's just 4. And ultimately, the minimum of 4 and infinity is 4. So it's a better choice to have the parent, or the node that comes before C in an optimal path, have A included. So A is going to become C's parent. And the total cost, our new upper bound on a best path to this vertex, is going to be 4. And we're going in alphabetical order for these vertices. So we see D. Now we're going to do the same thing. What did we just do there? So we know that the best we can do to get to A is 0, plus the edge weight to D is 7, versus the best we've done so far to get to D, which is infinity. So the winner is going to be 7. So we want the parent of D to be A. And then we want to mark the new best upper bound to D as 7. Okay. And then we're going to look at A to F, A to F. What is F's best upper bound so far? Infinity. What's the best cost to get to A? 0. And then the edge, traversing the edge is 5. 0 plus 5, that's just going to be 5. we can just see that A is the better choice. So we want F's parent to be A. And then the best upper bound we now have is 5. Okay, and that was the last vertex to process on A. So now we mark A as finished. So ultimately, what our goal is, off of each vertex, we want to say, from this vertex, can I improve all of the upper bounds for all of the adjacents neighboring this vertex? If I can, I'll update the parent and I'll update the new, better minimum upper bound. And if I do this for the whole tree, and every time I inspect a vertex, I guarantee I've already found the best way to that vertex. The start, we already know the best way to get to the start, which is doing nothing, because we start at the start. If we hold this rule across the whole graph, we're going to generate a globally optimal solution. Next, Dijkstra's will choose the unexplored vertex that has minimum cost. So right now, that is going to be the B. It has minimum cost, it has not been explored. Okay, so B's distance, best upper bound to B, is 2. How did we do that? We came from the parent of A. And because we came from the parent of A, that means that we traversed that edge and we decided that was the best choice. Who are B's edges? We have 4 edges coming off of B. We'll inspect all of them and we're going to try to improve our upper bounds using those edges. We're going to look at the A first. So we'll say min. Who's the winner here? We're going to say what is the best to get to A? It's going to be 0. Now we're going to compete that against what does it cost to get to B from the start, 2, plus the edge weight, which is 2, and then 4. So we see it's not a good choice to go through B for this path, because ultimately we're actually going to just go to B and then come back. That's not a good way to get to A. It's better just to stay at A. So this is kind of redundant, but it's still a check the algorithm will make depending on how we implement it. So we didn't do any updates there. Nothing was improved. And now we're going to look at D. Does this improve an upper bound? The best distance to D as of right now is 7. And then what's the best distance to get to B? It's 2. Plus the edge weight. The edge weight is going to be 6. B to D is 6. 6 plus 2 is 8. And then the minimum of 8 and 7 is 7. So we see that it's a bad idea to have the parent of D be the B. Because if the parent of D is B, B's parent is A. So we'd go A, B, D. That's a path cost of 8. The path cost of AD is just 7. So it's better not to take that path. We didn't improve anything. So now we're going to look at the E. What is the best way we can get to E right now? It's infinity. And then what is the best cost to B? It's 2. And then what is the edge weight between B and E? This is the cost. So on top of the cost to get to B, the best cost I found, I need to add the actual edge weight. So that's 3. So now I have 5. So it's actually a better idea to go through the B to get to E, because we never even reached it. So the parent of E becomes B, and the new distance upper bound to beat is 5. And then finally, we need to look at the G. So we're going to look at the G. So we need to compare infinity versus using the B as a parent. If we use the B as a parent, it's 2 plus the edge to G. B to G is 8. So do we make the choice to go through B? Yes, we do, because this is 10. And what do? We mark B as the parent of G, and then the distance upper bound becomes 10. Okay, so I think we explored all of the vertices off of B. Now we need to mark B as explored. We're finished. And now Dijkstra's is going to choose the minimum again of the unexplored vertices, the min distances. So far, the minimum distance turns out to be C in this case. So we're going to explore off of C now. So we have 2 edges coming off of C. We're not going to backtrack to the A because we know that's just redundant. The actual, if we coded this in a normal implementation, we would check that edge ultimately because it's a normal edge. We're going to loop over the edges, but that's not going to do anything for us, so we won't check that min. But we could improve our upper bound to F, so we're going to try that. So the cost to F right now is 5, and we want to see if we can improve that. So going through C. So the cost to C is 4 right now. If we made the jump to F, it would be 6. And ultimately, we see that 4 plus 6 is 10. Going through the C would not improve anything in terms of jumping to the F. We wouldn't want to jump to the F through the C. We could just go AF. So we're not going to take that. There's no more edges to explore, so we're just going to mark this as complete. And then we're going to take the minimum cost vertex that has not been explored yet. We have a tie between E and F, so we'll just choose the lower one in alphabetical order. So we're going to choose E. We're going to try to go off of E and prove all the upper bounds for the vertices touching E. So E has 2 edges coming off of it. We're now going to check if E can improve the path to G. So we're going to do a comparison. So the best upper bound to G right now is 10. What is the cost to get to E itself? That's going to be 5. And then what is the edge cost to jump from the E to the G? It's 7. So 7 plus 5 is 12. So if we do a comparison, the 12 versus the 10, it's better not to go through the E. It's better to go through the B. We're going to have a cheaper cost path. And again, this is the whole point of the video. This is why I'm trying to get across that these algorithms are making choices differently. We're going to look at Prim's, but Dijkstra's is making a decision where we want to minimize the path from the start. We're doing that at every vertex. Prim has a different goal, which is to minimize the edge that we add to the spanning tree we're growing. And we're going to see that. And now the minimum cost vertex is going to be F. So we have 4 edges coming off of F. We have the C, the A, the D, and the G. Can we improve the upper bound of 7? So we're going to say, what is the cost to get to F? It's 5. The cost to get to F is 5. The cost to jump to D is 1. And so this is 6. So it's actually better to go through the F to get to D than take that immediate path from A to D. So what we're going to do is mark the parent of the D as F, and then the new best upper bound is 6. And now let's try to improve the path to G. So the upper bound of G right now is 10, and the best we can do to get to F is going to be 5. So if we go through the edge from F to G, it's 6. So 5 plus 6 is 11. So ultimately that doesn't improve anything. That does not allow us to get to G any faster. So we're finished processing F, and now the lowest cost vertex that has not been visited is going to be D. So we have 4 edges coming off of D. So D came from F. So we won't just go to D and then go back to F. That would essentially be wasting time. That could definitely not be shorter to get to F unless there was a negative edge weight. Then that would make the min cost be better because that would reduce cost. That would take away a cost of path traversal. But we're just going to assume all the edges are positive. So we're going to look at A, B, and G. So can we improve the path to A going to D? The current upper bound on A is 0. And no matter what we do, the way we can get to D, it'll be max cost 6. And then we'll have to add the edge weight of 7. So that'll be 13. There's no way we can beat 0 because all of these edge weights are positive. So A is not going to be improved. So then we're at the B. How are we going to improve the B? The B is at a 2 right now. So the cost to get to D is 6. And what is the cost to traverse the edge between D and B? That's going to be 6. So we get 12, and we weren't able to find that better cost path. So now we're going to look at the G. Can we improve the upper bound on G, which is 10? Can we do that from D? Well, the edge weight's 6, and the cost to get to D is 6. So that's 12, and that does not beat 10. And that finishes up all edges for D, so we mark it as complete. And now finally, G. We're going to see if G can improve the path to anyone it's connected to. And actually, we can immediately just see, of course, we're going to still do the for loops if this was code, but we can see that we can't do that. Because look at all of the edges coming off of G. We're going to be going back and adding value. What is the cost to get to G? The cost is already 10. So I guess this is like the intuitive understanding. If the min cost to get to G is 10, and every single one of these optimized costs are going to be less than that, and we know that this is going to be positive, the only thing we can do is go up in value or stay at 10. But everyone's less than 10. So logically, it's impossible for us to even beat anyone in this list. Because all edge weights are positive, we can't improve on any of these guys because getting to G itself takes 10 in cost. So G, let's just mark it as finished. And then that is Dijkstra's algorithm run on this graph. Those are all the shortest paths. And let's actually draw out the tree. Because we have those parents, we can climb up this tree and actually visualize it. So let's create the shortest path tree. So those are the nodes, and when we get to prims, our job will be to connect all of these vertices. But in this case, we just are making a shortest path tree. So A has no parents, B has the parent of A, C has the parent of A, D has the parent of F, E has the parent of B, F has the parent of A, and G has the parent of B. And let's give the edge weights to these. If we did this right, this should be the shortest path tree produced by Dijkstra's algorithm. And again, these greedy choices were made by choosing the smallest cost vertex to use next. And if we continually choose that, then ultimately we're always going to be expanding these upper bounds off of minimum cost vertices that we're basing the next iteration of processing off of. And now we're going to look at Prim's algorithm, which has a different goal. Its goal is to choose the smallest cost edge on the growing minimum spanning tree that we are building. And this will be very clear by the walkthrough we do. So it's great that we saw Dijkstra's, and now let's look at Prim's algorithm. Let's see the minimum spanning tree. So first off, what is a minimum spanning tree? We're going to take all of these vertices and just move them over so we can look at them. We want a subset of the edges that is going to be minimum in cost, but connect all of the vertices. So ultimately, we want to form a tree, which is going to be a connected component, and this tree is going to have minimum cost. There's a lot of trees that we can create to connect these nodes. But ultimately, there's going to be certain trees that have minimum cost, and there might be multiple minimum cost trees. So we're going to look at prims. We're going to start off of the start vertex, and we're going to grow the minimum spanning tree greedily. We're going to make the locally optimal choice every time. What are the edges coming off of A? So what we're going to do, we'll keep dotted lines as what is Prim considering at every single step of the process of choice. And these are all of the edges that we want to build off of A to grow the minimum spanning tree. And we're going to greedily choose the smallest one. And the smallest one in this case is going to be that edge of size of cost 2. So we're going to connect the A and B. So our tree has 2 nodes. Our tree has the A and the B. We made that connection. But now that B is connected to the tree, we consider all of B's edges coming off of it. So I want you to think of this as soon as we add a node, it adds it's just like an array of vision. Because these 2 nodes added to this tree are going to have edges and other nodes they can see. Of all of the nodes that I can see from the given tree that I'm building, if I choose the smallest edge every single time, then ultimately we're going to build a minimum spanning tree because we're going to expand this out slowly, choosing the minimum cost edge possible at every step to add a node to this component or this tree we're building. So we're going to choose the minimum cost out of all of these. Which one is that? That's going to be the E. So we chose the edge that's the E. And now we're going to consider all of the edges coming off of E. What is the edge coming off of E? We already took the edge BE. Now we'll take EG. And so do you see how, as this tree grows, at all times, we will always consider all edges that can expand this minimum spanning tree. We will produce the minimum spanning tree because of the way we're considering everyone possible that can connect anything. So now we're considering everyone. Who's the minimum guy? The minimum guy is going to be 4. And then who is C connected to? C is connected to A, we already covered him, and then F. Right now our tree, where our tree is at, is C, A, B, E. We have 4 nodes connected, and we need to connect some more. So what is the minimum edge that can expand this tree, this connection of all of the nodes? Well, it's going to be the AF edge, so we'll take that one. And now that F is a member of the tree, we need to consider every edge coming off of the F. And now, well, we never even knew about this edge 1, that value 1 edge. If this were Kruskal's algorithm, we would immediately take that edge because out of all of the edges in the tree, that's actually the smallest one. And that's a different greedy strategy that we'll cover in other videos. But for this one, Prim just discovered about this. Prim just figured out that this 1 edge exists, this cost 1 edge, because of the way we're building this tree iteratively. So we're going to now take the FD edge. That's the smallest edge coming off of our minimum spanning tree. And now that D is a part of the minimum spanning tree, we can consider all edges coming off of him. So now we consider the edge with 6. And along the way, we need to, we're using this visualization, but in reality, these edges that connect a node already in the minimum spanning tree to a node already in the minimum spanning tree, those edges need to be not considered because we can't loop back into the tree. That's a redundant edge. So not keeping up with that might have messed up the visualization a bit, but ultimately, at every step, our goal is to, do you see how all of these nodes have a focus on G? G is the final node that is not in our minimum spanning tree. Because G is not in that, we're focusing on all the edges coming to nodes not in the minimum spanning tree. So before we had 1 node left, we were only focusing on what nodes are not in this minimum spanning tree that I can reach from nodes in the minimum spanning tree, pick the cheapest edge to get there. We're going to choose the cheapest edge to G, which we could go through the D or the F. We'll just choose the one in lower alphabetical order, which is D. And so now we don't want to connect back to the minimum spanning tree, so we're going to eliminate those edges from what can be considered. And that leaves us with a minimum spanning tree where all of the nodes are connected. All of the 6 nodes are connected by edges, and this actually forms a tree. And the reason we call this a minimum spanning tree is just a special kind of graph. And this is, you normally see trees formatted like this, so this is what the tree looks like. So ultimately, what is the cost of this minimum spanning tree? The cost of this minimum spanning tree is going to be 21. This was the distinction we drew. We walked through Dijkstra's, we walked through Prim's, and we saw the different greedy choices. The greedy choice of Dijkstra is to minimize the distance from the start to any given vertex. The greedy choice of Prim's is to minimize the edge that we add to the minimum spanning tree, to expand the minimum spanning tree, and not reconnect ourselves back to that same tree. Because we don't want to create a redundant edge. We want to only connect to new nodes, not in the tree. Let's minimize the cost to connect to them. So that is the difference between Dijkstra and Prim's. In other videos, we could look at the time complexity, but for this one, this was just a conceptual grasp of both of these topics. So if you haven't subscribed to the channel, subscribe to the channel, like this video if this was helpful. And that's all for this one.